Can you switch to the next slide, please?
I did.
Yeah, okay. In the next section, I'm now going to describe to you how we at Bayer have implemented the new pKa prediction tool for our end users. Now, we have defined some use cases. The first use case is addressed at medicinal chemists who might analyze pKa values in the context of chemical structures and determine the predominant charge state at pH 7.4, for example, for SAR analysis. The medicinal chemist gets a simplified table view on microstate pKa values resulting from the microstate equilibrium. Each macrostate pKa value is assigned to a specific ionizable atom, and the pKa is written as an annotation next to this atom. The assignments are determined by the most prevalent microstates. The predominant charge state at pH 7.4 is given in text form, switch ionic in the cetirizine example. The predominant charge state is also given in form of a charge state number, and you see a little table here which decodes that. And this is useful for the sorting of molecular spreadsheets according to the predominant charge state. Now, if you switch to the next slide, please.
Yes, I hit the button 3 seconds ago.
The second use case is for computational chemists. Computational chemists like myself could prepare large libraries for high throughput docking applications like virtual screening. The tool can adjust the protonation state of structures to reflect their dominant charge state at a given pH. And you might actually think, why is it important to also be able to change the pH now? You might actually run assays also under different pH conditions. Now, the fast calculation speed of more than 100,000 compounds per hour on one CPU allows easy processing of millions of structures. And and apart from setting the pH as input parameter according to biological assay conditions, I can also set the microstate prevalence threshold. Now, if this is set to 50%, then only the most prevalent microstate will be generated as an output structure. If I lower the threshold, for example, to 10%, then I would get, in this example, 2 output protomers for cetirizine, since now also the negatively charged microstate with a prevalence of 20% would land in the generated output SD file. If I lower the threshold once more to 1%, then I would get 3 protomers of cetirizine in the output SD file. So I'm quite flexible, and if I want to be very thorough, I can basically generate more output structures. Now, the third use case is for the in silico admit specialist who is developing in silico admit models. They can use the calculated predominant charge state at a given pH as input descriptor for model building. One can set the pH according to assay conditions. For example, log D can be measured at pH 2.3, an assay which is typically used by my colleagues from Biocrop Science. We measure buffer solubility, for example, at pH 6.5, the predominant pH of the lower intestines, and human plasma protein binding is measured at pH 7.4. If we set the pH to 2.3, we get positively charged as a predominant charge state in our example here at pH 2.3, while at pH 6.5 we get the predominant charge state switch ionic. One also gets the predominant charge state in form of a number and the charge state prevalence in form of a percentage number, so that they can be easily used as descriptors for model building. Now, in summary, one can say that merging public space and industry space for training has led to significant improvements in pKa prediction performance. External validation proved that following fundamental thermodynamic principles puts the pKa prediction of multi-project molecules on the right track, and different output formats options have been tailored to serve the special needs of medicinal chemists, computational chemists, and in silico admit specialists. Now, at the end of this presentation, I'm giving you an application example in form of a case study. This case study is from a research project I'm currently working on. The structures are made up of a core and a phenolic group attached to the left and a tertiary or secondary alkylamine attached to the right. Now, pKa measurement for the first compound here gives two pKa transitions, one at 4.7 and one at 9.4. So these are measured pKa. And 4.7 can be assigned to an aromatic nitrogen in the core, and 9.4 are assigned to the basic tertiary amine. Now, if you switch to the next slide, further derivatives with the same phenolic group and variations of the basic amine have been made and measured. And the basic pKa stays in the region between 9.4 and 9.6. And can you please switch also to the next slide? And this seemed quite feasible since all those amines initially could be regarded as highly basic. However, for the morpholin group, you can see on the right-hand side, second to the bottom, this was no longer feasible. Here we still measure 9.5, and of course a morpholin group is much less basic. The next slide, please. So which pKa predictions does ADMET predictor make for the first compound? The pKa for the aromatic nitrogen in the core is predicted spot on at 4.7. For the basic alkylamine, it predicts 8.6, and 9.5 is predicted for the phenolic OH as a weak acid. This means that the measured 9.4 pKa transition has to be really assigned to the phenolic OH, and the pKa transition for the basic alkylamine is simply not detected in our photometric UV detection system. This also means that ADMET predictor is in this compound class our only option to track the basicity of the alkylamine group and help us with optimization. And in this project, cell assay potency and target tissue penetration are important optimization goals, and the basicity of the alkylamine group plays an important role in this context. Finally, if you switch to the next slide, I would like to draw your attention to the predicted pKa 8.5 of the cyclopropylamine at the very right bottom. Now, the cyclopropylamine pKa values are currently predicted too high by ADMET predictor. And as a workaround, I recommend to take the predicted pKa for the corresponding isopropylamine derivative, 8.9 in this case, and subtract 1.6 to derive 7.3 in this case as the predicted pKa for the cyclopropylamine. The correction of minus 1.6 relative to isopropylamine has been derived from pKa measurements as outlined in the publication referenced in this footnote. And with this, maybe you switch to the next slide, our thank you slide. With this, I would like to thank you for your attention and hand back to Anu Sharma. Do you have the last slide as well? Yeah, okay.
Yes, I do.
Thank you, Mario. We have, well, before we start the question and answer session, I would like to tell you that we also offer 2 weeks of free trial license for ADMET predictor. If you're interested in testing all of the modules of ADMET predictor, which comes with physical, chemical, biopharmaceutical module, toxicity module, metabolism module, and the modeling module, then please let us know. That is the 6.5 version. But if you are specifically interested only in the pKa model, then please advise as well, so we could give you that version. So we look forward to hearing from you. And with this, I would like to open the question and answer session. We do have one question. And the question is, are higher members of basic centers in industrial set consequence of a number of compounds which could become kinase inhibitors?
That is a question for Mario.
Yeah, that's a big question. Well, not on, yes, kinase inhibitors, of course, would be a really good example, but if you think about it, pharmaceutical compounds, drug development candidates, they often have aromatic heterocycles with nitrogen atoms in them. And of course, basic groups are also weak bases, so all those heterocycles with aromatic nitrogens in them would count. And typically, of course, we wouldn't have multiple strongly basic groups in there. But this is probably, kinase inhibitors, good example. They have typically aromatic nitrogen for hinge binding. Yeah, that would be a good example. But also with other classes, you see that.
Thank you, Mario.
We need lots of functional groups. We need multiple functional groups to interact with our targets. So therefore, multifunctionality has something to do with that.
Thank you, Mario. There's another question. Is there possible intramolecular hydrogen bond for the phenolic OH in case study panel?
Yeah, so if this phenolic OH can form an intramolecular hydrogen bond in this molecule, no, it doesn't. It can't.
Thank you. So there's another, it's a question and there's a comment that great slides. Would it be possible to get a copy of them? And yes, I will be following up with you and I will send you the slides. And we will also have a copy of the webinar available on the Media Center section on our website.
We should actually mention that since we have given a conference talk last 2 weeks ago in Dubrovnik, those a reprint of those slides would be available from Robert anyway. And I will give a presentation which is pretty similar to this one next week on a conference in Germany. So I could also, after I've given that talk, send slides set out. But I think from this webinar you would be able to generate a PDF, right?
Yes.
Yeah, this is correct.
Yeah, that would be the best option. Then it's exactly this presentation.
Yes. Okay, thank you, Mario. And so there's one